number system, in which we will be discussing about a base of a number system, different bases, then conversion from one base to another, and the problems that will ask you to identify the unknown base. And we will also discuss base or addition in different bases, base 3, base 4, base 5, etc., base 16 additions. So the important topics are conversion of bases, identifying unknown bases, and base or addition in different bases. Then the second one is Boolean algebra. Boolean algebra. In Boolean algebra, we'll be discussing important theorems. The first one is a duality theorem or duality principle, duality theorem or duality principle. Okay. Then we'll be discussing different postulates of Boolean algebra along with De Morgan's law, or De Morgan's theorem. Then one important topic under Boolean algebra is simplification of Boolean algebra. Simplification of Boolean algebra. And we'll be using theorems to simplify Boolean algebra. And one of the important theorem is consensus theorem. So under Boolean algebra simplification, we will be discussing consensus theorem, right? Consensus theorem. So basically Boolean algebra consists of three theorems: duality theorem or duality principle, De Morgan's law, and consensus theorem, right? Then the third topic is min terms and max terms. Min and max terms. Min terms and max terms. Min terms and max terms of a given function. How to identify the respective min or max terms. Which are the min terms of a given Boolean expression, and also how to find the min terms corresponding to a given expression. Or the other way, how to identify the Boolean expression from the given min or max terms. Min terms will specify the condition for function f equal to 1. Similarly, the max terms indicates the condition corresponding to that function f equal to 0. Min and max terms, and their simplification using min and max terms. How to identify the min terms of a given function, how to identify the min terms of a given logic diagram. Right. Then we will get into logic gates. Logic gates. We will be discussing basic logic gates, how to interconnect the different logic gates, how to find the output expression of a gate network, how to identify the min terms corresponding to the output of a given logic gate diagram. Then we will be discussing about identifying the output function of a given logic gate diagram and the minimum number of logic gates required to implement a particular Boolean functions. And we will be discussing about dual of a given gate, dual of an AND gate, dual of a NOR gate, etc., etc. Also, we'll expand the concept of duality principle or duality theorem that we are going to study in Boolean algebra into the logic gates, right? Then we will be discussing about combinational circuits. Of course, logic gates are also combinational circuits. So combinational circuits or combinational logics, in which we'll be discussing about two important topics. They are multiplexers or simply mux and decoders. Multiplexers and decoders. Right. In multiplexers, we'll be discussing about 2 by 1 multiplexer, a basic multiplexer with a two number of inputs and one output, 2 by 1 mux, then 4 by 1 mux, etc., up to 2 power n by 1 multiplexer. Also, we will be discussing how to implement Boolean functions using a multiplexer. Implementation of Boolean functions using multiplexers. Access. Also, how to implement an higher order multiplexer using lower order multiplexers. Let us say how to implement a 2 by 4 by 1 mux, 2 raised to 4 by 1 mux using 2 by 1 muxes, or how many 2 by 1 muxes are required to implement a 2 power 4 by 1 mux or 16 by 1 multiplexer. And we will conclude that all Boolean functions can be implemented using multiplexers. And we will deduce a condition to implement an n-variable function, n-variable Boolean function using only 2 by 1 multiplexers. Or we will answer the question, how many 2 by 1 muxes are required to implement an n-variable Boolean function. The second important topic under combinational circuits is decoders. Decoders. Basic properties of a decoder. Output expression of a decoder. How to implement higher order decoders using low order decoders. Let us say one example. If we have a 2 by 4 decoder with us, how to implement a 4 by 16 decoder. Right. Also, we'll try to implement Boolean functions using decoders only. Right. How to implement a given Boolean function using decoders. Or the other way, how to implement different min terms using a given decoders. Other than this, under combinational circuits, we will be discussing simple topics like adders, subtractors, magnitude comparators. Magnitude comparators. Under adders, serial adder, parallel adder, BCD adder, and carry, look ahead adders, etc. Then we'll get into sequential circuits. Sequential circuits. The topic is sequential circuits. or sequential logics. Right. Here we will be dealing with different flip-flops. Prior to that, different latches. Okay, latches. Then flip-flops, different flip-flops. Basic difference between a latch and a flip-flop. And what are the different flip-flops? And flip-flops state diagram of a given flip-flop, along with the characteristic equation of a given flip-flop. How to identify the characteristic equation of a given flip-flop using its own truth table. Okay. After this, we will get into one important topic under sequential circuit, that is conversion of flip-flops. Conversion of flip-flops. So basically, we are having a SR flip-flop, JK flip-flop, T flip-flop, and T flip-flops. Then how to convert one flip-flop into another. Let us say SR flip-flop into a JK flip-flop. Similarly, a JK flip-flop into, let us say, T or D flip-flop. Once we are comfortable with the flip-flops, we will get into counters. Counters. Counters are application of a flip-flop. We can interconnect flip-flops, different flip-flops or similar flip-flops differently, so that we'll have different types of counters with a different modulus. So basically we'll define what is a modulus of a given counter. Okay. Basically, you're having two different kinds of counters. One is a synchronous counter, and asynchronous counter. Synchronous counters will be having the same clock signal for all flip-flops, whereas asynchronous counters will have different clock inputs. Output of a flip-flop is connected to the clock input of another one. That kind of circuits are called asynchronous flip-flops or asynchronous counters. Those circuits in which clock signals are connected together to all flip-flops, we'll call it as synchronous flip-flops. Or sorry, synchronous counters. And you can expect questions from counters basically for identifying the modulus of a given counter. They will give you the diagram of a counter, that is an interconnection of a flip-flop. Then you should identify the counting sequence. Thereby, you should identify the modulus of a counter. Modulus means the different states of a counter, right? Or you may ask to find the next count corresponding to a given count, right? After this, we will be designing one or two counters based on our requirement. Okay, design of counters. Design of synchronous and asynchronous counters, right? We'll be discussing different counters: ring counter, Johnson's counter, Twister ring counter, etc., etc. Mode 3, mode 4, mode 5, etc., etc. Once the sequential circuits are completed, the second application of flip-flops are memory. So next we will be discussing about memory, right? What is the total capacity of a memory? What will be the starting address of that particular memory if the ending address is given? Or the other way, if starting address is given, what will be the ending address of that particular memory, right? And how to identify number of locations, and also how to identify the number of address lines required to address a particular memory. Then we will be discussing about three modules. They are programmable logic arrays, PLAs, and programmable array logic, PAL, and read-only memory, ROM. And then we'll wind up the subject, right? These are the topics we are planning to cover, and expected number of hours is roughly 28 to 30 hours. Of course, that will depends on your pace and my pace and correlation between both of us. So roughly it is around 28 to 30 hours. And of course, you'll be thinking about expected number of questions from different streams, right? So for all streams other than AAA, you can expect around 5 to 6 marks. This is based on recent papers. This is for EC stream, computer science, CSE, and instrumentation. AAA, you can expect 1 marks less, that is 4 to 5 marks. And it may vary, it may go to 6 to 7 for EC, CSE, and instrumentation, and 5 to 6 marks for AAA. Usually, it will not come less than 5 for EC, CSE, instrumentation, and it will be always at least 4 marks for AAA, not less than that. Okay, these are the overview about the subject, digital electronics, and we'll be keeping the same order. We'll start from number system, we'll go the same order 1, 2, 3, 4, then combinational circuits, then comes sequential, then we'll wind up after discussing memory. And the most important topics under this subject are multiplexes are most important. Then comes logic gates. Then comes sequential circuits. All right, so let me number it. 1, 2, 3, and the fourth one is number system. Then comes Boolean algebra and simplification of Boolean algebra. Okay, so the topics are related actually. If you are comfortable with the Boolean algebra min and max terms, you can understand the subject in a better manner, right? And today we'll be discussing about number system. That is an independent topic. Okay, we'll not take number system into Boolean algebra, min term and max terms, logic gates, etc. It's an independent topic, but all other topics are important and related. And here, while discussing min and max terms, we'll be spending much time on this min and max terms, and that is most important to understand the subject in a better manner. Okay, I would say basic understandings of min and max terms will help you to understand the topics like logic gates, combinational circuits, and sequential circuits. So this is very, very important. Basic understanding of min and max terms are required to understand the other topics, right? Is that clear? Any other queries? And please keep in mind that these are expected marks based on last year papers. It may go up and it will not come down from 5 or 4 usually. Okay. Right. Any other queries? Is that clear to all? Any other informations are required? Yes, please reply through chat box. Yes. Otherwise, I won't be getting the feedback. There is no face-to-face contact. Okay. Is that clear? Right. So we are about to start number system. Right. All right. Okay. Myself is Sapish. I am assigned to teach you digital electronics. Okay. And regarding your doubts, you can ask any doubts in the class with respect to the subject. If I'm able to clear that, I will clear it in the class. Otherwise, I will postpone. If I don't know, then I will say I don't know. Okay. So you have the freedom to ask your doubts always. Okay. No restrictions. Don't bother whether I can answer or not, but you can always shoot your questions. All right. Okay. Anything else? Let me ask you, anyone from our third year batch, third year students? Anyone? Anyone who's studying third year engineering? All right. Okay. Anyone who completed the course, graduation? Yes. Okay. Yeah. Okay. So we have, yeah. So we have different varieties. No problem. Okay. How many are you doing in your fourth year? I think fourth year exams are over, right? Fourth year exams are over, completed theory exams. Yes. Completed. All exams are completed. Yes. Okay. Right. Okay. 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 So let me tell you one more thing. You are spending time on your GATE coaching classes. Okay. So there will be pre-final year students and those students just completed their BTech, and there may be some of you maybe completed your graduation 1 year or 2 years ago. No problem. Okay. So if you are putting some effort to learn the subjects, can be any subject, right? Please ensure that you are putting your maximum efforts. Okay. And we have a limited time, 6 to 7 months. Okay. If you're putting your efforts sincerely for the upcoming 6 to 7 months, okay, you will be able to grab a good job, right? And that will help you in your future life. Okay. So it's just a matter of 6 to 7 months of hard work, get a good job, get a decent job, right? Then enjoy your life. Okay. So you are going to study, you are going to put your effort for 6 to 7 months only. Okay. Then you have so many years, 50 to 60 years. Then remaining your 50 to 60 years, you can live peacefully and happily. Okay. So you just concentrate another 6 to 7 months, prepare well, Right. Write exams well. That may be private sector, public sector, higher studies, researches, doesn't matter. Put your maximum effort, achieve it, then live your life peacefully and happily. Right. Please note that for a peaceful and happy life, money is important. That is a primary requirement. Okay. Right. So at least you should get an offer at least for 8 to 10 lakhs, right? So that you can live happily. Okay. So learning is important. Put your maximum effort during a particular period, then enjoy the rest of your time. Okay. So that you please keep always in your mind. Okay. You are going to put your effort, you are going to avoid all your other enjoyments for a limited period only, 6 to 7 months. Then you can go for all kinds of enjoyments after getting a good, decent job. Okay, so that you keep in mind. So if you don't have any other queries, I will get into the subject. Shall I start? Yes. And usually we'll be taking a break after 1 hour. Okay. So we'll break by 6, then by 7, and in between there is a prayer time, so we will adjust accordingly. So we'll make a first break after 1.5 hours. 6:30 we'll break, then we'll meet again by 6:45 or 7. Okay, right. So let me start. The first topic is number system. Number system. You can expect one question from this. Okay, and it is very easy to answer. Right. For proper understanding of a number system, we should identify what you mean by a base of a number system. What is a base of a number system? We have a familiar number system, that is decimal, base 10. Okay, so a decimal number system has a base 10. What do you mean by base 10? A base 10 implies in that system, decimal system, we are using 10 simples. They are 0, 1, etc. up to 9. A total of 10 simples. 10 simples. So the base of any system, any number system, is nothing but the number of total simples used in the system. For example, in your binary, base 2 or binary, we are using 2 symbols. They are 0 and a 1. Right? And our famous hexadecimal system, base 16. Then we should use 16 symbols there. Okay. And those 16 symbols are 0 up to 9, 10 symbols similar to decimal. Then 6 more are required. They are A, B, C, D, E, and F. That's a base 16 system. If it's a base 4 system, base 4, you'll having a symbols from 0, 1, 2, and 3. 4 symbols. Base 8, base 8, we're having a symbols from 0 to 7. 8 symbols. Right. If you're having a base 12 system, let us say base 12, right? You will be having symbols from 0, 1, etc. up to 9, 10 symbols. Okay. Plus, we require 2 more symbols. You can call them either XY, alpha, beta, AB, etc., etc. Let me call them as alpha and beta. right? And the decimal equivalents are alpha corresponding to decimal 10, beta corresponding to decimal 11. Similarly, in your hexadecimal number, the symbol A corresponding to number 10, decimal equivalent 10, B corresponding to decimal number 11, C 12, D 13, E 14, and F 15. Right? In all these cases, you can observe that the highest simple, highest simple, highest simple, having a decimal equivalent of base minus 1. Here it is base 4. So the decimal equivalent of the highest number will be base minus 4. That is 3. 4 minus 1 is 3 here. 8 minus 1 is 7. 10 minus 1 is 9, highest simple. In the case of hexadecimal system, this is hexadecimal base 16. I'm having highest number or the decimal equivalent of highest simple, that's equal to base minus 1. Base is 16. 16 minus 1 is 15. 1, 5. So the decimal equivalent of a highest simple used in any base is nothing but base minus 1, right? Or the decimal equivalent of a simple that gives us the maximum value is base minus 1, right? In your binary system, we are having two symbols only, 0 and a 1, and base is 2. The highest symbol will be having a decimal equivalent base minus 1, that is 2 minus 1, that's equal to 1, right? So that is a base, and base cannot be 1, base cannot be 0, because if base is 1, we are having only one symbol 0, and base is 0, we don't have a symbol. Okay, so base is always greater than or equal to binary. A system with the least base is a binary system. Base can be 13, 14, 15, 20, 21, etc., etc. Doesn't matter. But the least value is 2. And that's our binary system, right? Okay, then next topic is conversion of bases. How to convert a number from. Did you copy this last slide? Then, if you have copied, you just type C. If not, I have to wait for that. Then you should type W for wait. I will wait. Okay, copied. If you are copied, just type C. Okay, right. So next topic is the conversion of bases. Conversion of bases. Right. Right. How to convert from one base to another base. Okay. So let us take decimal to other base. Okay. Let us take an example. Let us take a number 5 in decimal. And I would like to convert into base 3. Let us say xy base 3. X and y base 3. And x and y are simples used in base 3. Okay. So the decimal number 5 has to be converted into a base 3 equivalent, right? Or they may ask you what is the base 3 equivalent of a decimal number 5. Okay. And what is the procedure to convert from decimal to any other base? To convert a number expressed in decimal to any other base is very simple. You take that number is 5, then divide that number with the required base, that is 3, right? So 1 3s are 3, balance is 2. Okay, it's a continuous division, but we cannot divide 1 with 3. So that 3 I should, sorry, that 1 I should write it as a balance, right? Then I should express this from bottom to top, bottom to top. That is, your x will be 1 and y will be 2. Bottom to top, 1, 2, base 3. So 5 decimal is equivalent to 1, 2, base 3. Right? It's very simple. Continuous division to convert a decimal number to any other base that is less than decimal. Right? 3 is less than 10. So continuous division with 3. So if you would like to convert decimal 8, into, let us say, base 4. What will be your answer? The decimal equivalent, sorry, the base 4 equivalent of a decimal number 8. What's your answer? So you should divide the number, that is 8, with the required base, that is 4, right? 2 4s are 8, no balance, 0. And you cannot divide 2 with 4, so I should write as such, right? So 20 base 4, right? So decimal 8 is equivalent to 20 base 4. Okay. So you should divide continuously, then write from bottom to top, right? Let us convert the other way. Let us convert a number, let us say 5, 5 in base 6 into a decimal equivalent, right? Base 6 to decimal, base 6 to decimal, lower base to higher base. 10 is greater than 6. How to convert that? How to identify the base 10 equivalent of a number 5, 5, base 6, right? What's your answer? How to convert that? So that is also very simple. It's a continuous sum of individual products, right? Here we are having 2 digits, one, another one, 2 digits. So you take first simple, that is 5 here, multiplied by base. Base is 6, power 1. Here 1 is the number of digits minus 1. So this one is nothing but n minus 1. Here n is the number of digits, that's equal to 2 here. 2 digits, 5 and 5. Then sum with another digit multiplied by base power 0. That is n minus 2. Number of digits minus 2. So we are having only 2 digits. So we'll have 2 terms, right? So that will give me 5 into 6 are 30. 30 plus 5, 35. 35 decimal. So to convert from lower base to decimal, you should take a continuous product, then add. To convert from decimal to any other lower base, you should divide it continuously, then express the number from bottom to top, bottom to top, right? Bottom to top. Okay, suppose you are having n number of digits in, let us say, base R. We are having digits A, B, C, etc. N digits. Okay, n digits. n digits, and the number is in base, let us say base r, right? I should convert that number into decimal equivalent, right? Decimal equivalent. Similar to this, decimal equivalent. Instead of 6, the base is r. Here I had 2 digits. Here I am having n number of digits. So n digits. N number of digits. So to convert into decimal equivalent, you pick the first simple, that is a here, right? Multiply with the base power total number of digits minus 1, right? Here it was 2 digits, 2 minus 1 was 1. So r power n minus 1 plus second digit multiplied by r power n minus 2 plus third digit multiplied by r power n minus 3 plus etc. expressed in decimal, right? So continuous division and addition of continuous product to convert base r to base 10, continuous product and addition, base 10 to lower base, continuous division. Okay, is that clear? Clear or no? Right? Is that clear? Yes. If I am going too slow, please let me know. I will increase the pace. Okay. So you'll be having different pace, students. So if it's too slow, please let me know. I will improve. Okay. Right. The last question is very simple. We are having a base R system. Okay. Right. Base R system. Okay. In base R system, I have used the symbols A, B, and C, etc. I'm having n number of symbols. Right. Right. That will be same as base. Number of different symbols in a system is called base of that system. So if base is R, of course, I will have R symbols, right? So n should be equal to R. So it doesn't matter. So to convert into decimal equivalent, you take first digit, multiply with that particular base, power total number of digits minus 1. So n was the total number of digits, n minus 1, plus second digit multiplied by same base with the power n minus 2, where n is the number of digits. Okay, number of digits of your base R number. Then if you're having a D, E, etc., you can add it along with the D multiplied by R power n minus 4, etc., etc. Then if you're adding together, you will get a number that will be in decimal 10. Right. If R is not less than 10, that is a good question. If R is not less than 10, we'll have different symbols. Let us compare a base 16, right? Base 16 and a base 10. So here we have assumed that 10, right? R is less than 10, right? If you're converting from hexadecimal to decimal, that is 16, base 16 to base 10, right? Let us say I have a number, let us say F, a hexadecimal. And what is the decimal equivalent? So if you're dealing with hexadecimal number, our symbols will be from 0, 1, etc. to 9. Then A, B, C, D, E, and F, right? So this corresponding to decimal 10, okay? This is decimal 11, decimal 12, right? Decimal 12, decimal 13, decimal 14, and decimal 15. To a simple given in higher base, you will have a symbol or an equivalent value in decimal. So this is 15 and decimal. You need not convert. It's readily available, right? So if this base is less than this one, so this system will be a subsystem of this system, right? And this is corresponding to decimal, okay? Decimal is a subsystem, right? So you can select the equivalent from that system, F corresponding to 15 decimal. If you're converting that 15 to hexadecimal, 15 decimal to hexadecimal, right? Hexadecimal, right? Here, 10 is less than 16, right? Then you should divide it continuously, right? Or if you are going to find the decimal equivalent of a number, let us say 1, 2 hexadecimal, and its decimal equivalent base 10. Then you should multiply with the base 16. First digit is 1 multiplied by base is 16. We are having two digits, so 2 minus 1, n minus 1, 2 minus 1 is 1, plus second digit multiplied by base power n minus 2, 2 minus 2, that is 0. So I'll have 16 plus 2, that's equal to 18 decimal, right? So if you have a simple corresponding to given number in decimal, you can directly pick that. So decimal 10 is equivalent to base 16 simple F, right? And in your question, they will specify both bases. We'll have problems based on that. So both bases will be given to you, right? Or they will give you one equation and you should identify the unknown base, right? Is that clear? Girivarad, Adarsh, and Srinath. Is that clear? Yes. Okay. So we'll have few problems, then you'll be familiar with. Okay. Before that, we'll have a different problem based on number system. Okay. So let me write the question number 1, first question of today's class. Identify the decimal equivalent, the decimal equivalent of highest number, okay, highest number in base 3 using two digits. You're having a base 3 number, and you should identify the decimal equivalent of the highest possible number in base 3 using how many digits? 2 digits. You can use 2 digits. You should express the highest possible number in base 3 system using 2 digits, and you should find the decimal equivalent. right? So base 3 system implies the highest possible simple is base minus 1, that is 2, and you have a freedom to use 2 digits, so 2 will be the highest number in base 3 that uses how many digits? 2 digits. And you're asked to find out its decimal equivalent. How much is decimal equivalent? How much? 2 multiplied by 3 power 1 plus 2 multiplied by 3 power 0. So 6 plus 2 will give 8 decimal, right? Very good. Then what will be the decimal equivalent of another number? Let us say 3 in base 4. How much it is? 3 multiplied by 4 power 1 plus 3 multiplied by 4 power 0. So 12 plus 3, 15 decimal, right? Then let us have one more question. Decimal equivalent of 4 in base 5. How much it is? 4 into 5, 4 multiplied by 5 power 1 plus 4 multiplied by 5 power 0. So 20 plus 4, 24 decimal, right? Then similarly, in base hexadecimal, base 16, highest symbol is F. So highest number will be FF using 2 digits. Base is 16. And what will be its decimal equivalent? What will be the decimal equivalent? So this F corresponding to 15 decimal, 15 decimal. Okay. So the equivalent will be 15 multiplied by base power 1 plus another F 15 multiplied by base power 0 decimal. Right. So that will give me 15 into 16 plus 15. Right. How much it is? Is it 255? Base 10? Yes. Okay. Then it will be tedious if we are having more digits, more number of digits. Let us say to identify the decimal equivalent of a number, let us say 555 base 6. What will be the decimal equivalent? Right. So for that, you can directly write it by observing the number. Let us check that. 2 to base 3 was 8. Here the base was 3. So 8 is nothing but 3 square minus 1. Second case, base was 4. So that is 4 square minus 1. 16 minus 1 is 15. Right. Here the base is 5. So 24 is 25 minus 1. 5 square minus 1. Right. Here the base of the system was 16. Right. So 16 square minus 1 is 255. Right. So in general, you can write it as r power n minus 1. Here r is the base and n is the number of digits. Right. So in a particular base, if you are using n digits, 2, 3, 4, etc., n number of digits, to identify the decimal equivalent of in highest number, highest possible number in base r using n digits, take the power of n, r power n minus 1. Right. So Aravind is asking, sir, so can we also generalize this as base power 2 minus 1? Base power 2 of
Sir, it
n.
was the one that you explained just now. I was
Yeah.
asking that doubt. before you
No,
explain this part.
now it's clear.
Yes, sir.
Okay, thank you. Right, so don't forget this. You need not calculate like this, right? And of course, your options are in the form of this one, r power n minus 1, right? Suppose they are asking you triple six base 7, okay? And what is the decimal equivalent? And you will find an option that 7 power 3 minus 1. So you can go for that. You need not do this, right? So base power number of digits minus 1 will be the decimal equivalent of the highest number using how many digits? N number of digits in base R, right? Okay, I think that is clear. So you please try to learn in the class itself, okay? You may not get the time to study at your home. So let us learn in the class itself, okay? Right? I think this is clear, right? Okay, right, right. So while converting into another base from decimal, we skipped the fraction part. Okay, so let us have a look into that. So here, next question, question number 2. You should convert the number, decimal number 0.125 base 10 into its equivalent binary number. Binary number. Binary number. So to convert a fraction number expressed in decimal into a base that is less than decimal, you should continuously multiply that given number, that is 0.125, with the required base, that is 2 here. So multiply with 2. So I'll get 0.250. Again, we should multiply with the same base 2. I will get 0.500. Again, you should multiply with the same base. I will get 0, 0, 0, and a 1. Then I cannot multiply it further because this is already 0. Then to write the binary equivalent, I should follow the other order, top to bottom, right? Here it was from bottom to top, right? And here it is from top to bottom. A fraction decimal into an equivalent binary number. And while writing that, you should not include this, right? So you can write it as top to bottom, this value, and this value. So they are 0, 0, 1. And you should put a point before this, 0.001, 0, right? Top to bottom, and this 0 is not part of our result. So that is a part of our given number. So I should take from here onward 0, 0, and a 1. Okay. To convert a fraction decimal number into base to equivalent. Let us convert the other way also. You are given with 0, 0, 0, 1, 0.001 in base 2, and you are asked to convert into its decimal number. Decimal number. Right, Arvind asking a query that. So should we multiply until we get a number greater than 1? It's not like that. Until you are getting all digits here zeros. because further multiplication is not possible. We are multiplying this part, fraction part, fraction part, fraction part. Once entered digits are zeros, we cannot multiply it further. So you should multiply until you are getting all digits right side of this point zeros. Okay, right. Some cases never you will get a complete zero. It will repeat, repeat, repeat. So never it goes to zero. Then you have to write the numbers. Let us say 0, 0, 1, 1, 0, 1, 0, 1, 0, like that. You should write. It never ends. Okay, in some cases, but not in all cases. Okay, is that clear, Ravind? You should multiply until you are getting all digits here right side of this part zeros. Okay, right. So if you're asked to convert a binary number into a decimal equivalent, a binary fraction, okay, into decimal, it's similar to your other conversion. That is, if you are asked to convert 110 base 2 into a decimal number, what we will do is we will take first digit, right, multiplied by base power, total number of digits minus 1, 3 minus 1, 2, right, plus addition, another digit, 2 power 1, plus another digit, that is 0, 2 power 0. So I will get 2 power 4, 4 plus 2, 6 decimal, right. So if you are having a point here, you can extend this. How to extend that? You should multiply the other digit, that is 0 here, so 0.0 here, multiplied by 2 power, you are up to 2 power 0 here, so 2 power minus 1, plus the other digit 0 multiplied by 2 power minus 2, plus the third digit is 1 multiplied by 2 power minus 3. Right, so first part is 0 plus another 0 plus 1 by 2 power minus 3 is 2 power 3 is 8, so 1 by 8. So that's equal to 0.125. Right, so in general, if you're having a number A, B, C, D dot E, F, G, right, let us say in base R, to convert into decimal, okay, similar to this, it was in a binary, only fraction part, right. So the procedure is take the first digit, that is A here, right, A here, count the number of digits here, 1, 2, 3, 4. So A multiplied by R power n minus 1, 3, plus B power B multiplied by R power 2, plus C multiplied by R power 1, plus D multiplied by R power 0. Then you should be careful. I have a point here. You should not place a point here. Then E multiplied by R power minus 1 plus F multiplied by R power minus 2 plus G multiplied by R power minus 3. It is wrong. You should not put a point. It's actually an addition, continuous addition. You please keep in mind. So this is an addition plus, right? You should add it, right? So here I should add it 0 plus, right? Because here I am having a 0 digit. So 0 plus. So 0 plus. So please don't make a mistake. So this is a plus sign. It's a continuous addition. You should not put a dot instead of this addition. That is an addition, right? Suppose you have an example like a 3, 4 base 5, or let us say 3, 4 dot 2, 3, right? Base 5. If you're asked to find its decimal equivalent, right? You should take it like 3 multiplied by base power 1 plus 4 multiplied by base power 0. You should put an addition here. Add plus. Next digit is 2 power base power up to 0. You should subtract one more. So we'll get a minus 1 plus 3 multiplied by base power minus 2. And this will be your decimal equivalent. So please take care of this addition. Okay, is that clear? Yes. Any queries? So right now you are comfortable to convert a decimal number to any base system, right? A number expressed in any base into back into decimal. Okay, right? That includes fraction also, right? Right. So lower base to decimal is continuous product, even though you are having a fraction here. It's a continuous product and addition, right? Whereas if you are having a number like this, you need not bother about fraction. The fraction part is 0. So you have only one term. So plus, you can put a 0. Okay. So continuous addition of individual products, right? In other case, if you are asked to find the binary equivalent of a fraction decimal, you should multiply with the lower base until you are getting all digits 0. Similarly, if the number is not fraction, if you would like to convert into the other base, you should continuously divide the given number in base 10 or higher base with the 3 required base. Okay, so I'm closing that discussion there. So the important points you should remember from this is you should put an addition here. Don't forget that. And this also r power n minus 1 will be the highest possible number in base r system using n number of digits. Okay. You may have a question like that also. What is the decimal equivalent of an highest possible number, decimal equivalent of a highest possible number using n number of digits in base r, and that's equal to base r power number of digits minus 1, decimal equivalent of an highest possible number in base r using n number of digits. So please don't forget these 2 points. And the fundamental principle is if base is 16, we'll have a 16 minus 1, 15 decimal as the highest equivalent, right? And total of same 16 simples, including 0 to 15. Total count is 16, same as your base. Okay. So I'm moving into the other slide, right? Did you copy this? It's completed. So let us get into the problems based on what we have learned so far. Okay. Right. So please write down the question. I have a number, let us say 3, 2, base r is equal to 14 decimal, right? Question number 3, 14 decimal. Identify the value of base r. Identify the value of base r. Options are given. 3, 4, 5, and 6. Right, very good. George is answering 4. Ashok 4. Meenakshi is also answering 4. Sitara Sajit is also answering 4. Right, very good. Very good. What about others? Right. Okay. Very good. Right. Okay. Okay. Very good. Okay. Let us have another question. Right. Right. Question 4. Question number 4. Right. I have a number. Let us say 1, 2, 3 base R plus 5, 4, 3 base R equals 6, 6, 6 base R. Find the value of base R. Find the value of R. Options are given. 4, 5, 7, none of the above. So you have one equation, left hand side and right hand side. They are matching. Equality sign is given. Equal. So the unknown value is R. All right. Nafis is answering 10. Aravind answering none of the above. Let us check that. So you should convert this into a decimal first. That is R squared plus 2R plus 3. All right. Because we should bring R variable into our equation. So that is the only possibility. Converting into decimal. Plus second term is again 5R squared plus 4R plus 3 decimal base 10 base 10 equal to the right hand side is again 6R squared plus 6R plus 6. So we have R square here and 5R square here. So that will be 6R squared. 2R and 4R will be 6R. 3 plus another 3 will get 6. So this equation will hold for all values of base R. This is true for all values of base R, right? But you can note that given option base is 4 is given, base 4 is given. Look at this 4 symbol I have used in base R. So R cannot be 4. R cannot be 5 because I have used a symbol 5. I have used a 6 also, right? So symbols will be always less than the base. So base cannot be 4 or 5. So it can be 7. But it is true for all values of R. So the actual answer should be R should be greater than what? Greater than highest symbol in the equation is 6. Greater than 6. Or R should be greater than or equal to 7. Sorry. Yeah, R should be greater than or equal to 7. Right? So none of the above is
So,
right choice here, right choice. But actual answer will be R greater than 6 or R greater than or equal to 7.
hello
Yes.
sir.
Yes.
Sir, ఆ 666 బేస్ 6 లైన్ ఏమో ఆర్ క్యూబ్ మైనస్ 1 అనేది కూడా
666 base r. Right. Yeah, you can write r cube r, not r cube, right, r cube minus 1 in decimal. That is also true, right? R cube minus 1 in decimal. Right, that is also true. So we'll have 6r square plus 6r plus 6. 3 plus 3 is 6. Will be equal to r cube minus 1. That is also true. So this equation will become minus r cube plus 6r squared, then plus 6r plus 6 plus 1 equal to 0. And here you're assuming that base is r, right? You can identify the value of r. And that will be true for all values greater than 6 that you can verify. That is also true. Okay, Princey? Clear? But solving that will be difficult, I guess. You can solve it, no problem. Right? Okay. So we have a lot more problems based on this. So before that, let me get into base R addition, then we'll go for a break. Okay. So base R addition. Base R addition. Base R addition. Right. Base R addition is very simple. Right. Suppose you are asked to add two numbers in, let us say 3, 2, base 4, and 1, 2 in base 4. You are asked to add these two numbers and you are expecting your result in base 4. Because two numbers are in base 4 and the base 4 addition should give you a result in base 4. And what will be the result? Base R addition. Right? Addition in any base. Base 2, base 3, base 4, etc. Base 10, base 11, base 16, hexadecimal addition, etc. etc. And what's your answer? 3 to base 4 plus 1 to base 4. So if you're confused, just go back to your basics. That is a decimal addition. You're comfortable with a decimal addition. Let us take one example. Let us take 3, 8 plus 6, 7. Decimal addition. Base 10, base 10. And you're expecting a base 10 number here. Right, Srihari Suresh is replying with the 233, right? Very good. 233. Let us check that. Okay, very good. So let us check. So let us have a decimal addition first. 38 plus 67. 8 plus 7, 15. Will we write 15 here? No, we will write 5 here. 8 plus 7 is 15. Instead of 15, we will write the number 5. Why we are not writing 15? In decimal, we are having a symbols up to 9. We don't have a symbol corresponding to 15 decimal, right? So if that is the case, I should extract 5 from the result 15. 8 plus 7 is 15. How to get a 5 from 15? You should subtract 10. So 8 plus 7 is 15. We don't have a symbol corresponding to 15 in decimal. So I'm subtracting the base 15 minus 5 is, 15 minus 10 is 5. So I'm writing that 5 here and I'm taking a carry. Why I'm taking a carry? I have subtracted a 10, right? Then I should compensate that. Okay. Please recall that 20 and 30 in decimal are differed by 10. If you are adding one digit to the next higher bit, instead of 2, if you are writing 2 plus 1, you are actually adding 10. So you are subtracted a 10 from this addition, 8 plus 7, 15. Instead of 15, you wrote it as 15 minus 10. So you should compensate that subtraction. So you are adding a carry 1. So 3 plus 6, 9 plus 1, 10. Unfortunately, again, for 10, I don't have a simple. So I should subtract 10 from the result 10. 10 minus 10 is 0. For that subtraction, I should add a carry. So it is nothing but 105 decimal. Right. Maniraj answered here. Very good. 110. Very good. So let us take this addition. Okay. 2 plus 2. Oh, that will be 4. And it is a base 4 addition. Base 4, I have symbols from 0, 1, 2, and 3. 4 symbols up to 3. So 2 plus 2 is 4. I cannot write 4 here because 4 is not a valid symbol in base 4. So I should subtract the base. What is the base? Base is 4. So 2 plus 2, 4. 4 minus 4 is 0. To compensate that subtraction, I should take a carry to the next higher digit. So 3 plus 1 is 4, 4 plus 1 is 5, 5 is not a valid symbol in base 4. So I should subtract 4. So 5 minus 4 is 1, right? Then for to compensate that subtraction, I should take another carry. So it's a 110. 2 plus 2, 4, 4 minus 4, 0, carry 1. 3 plus 1, 4 plus 1, 5. 5 minus 4 is 1, carry 1. And while adding carry, you can assume by default these digits are 0. So 1 plus 0 plus 0 will get a 1. So it's a 1, 1, 0 base 4. Right. Right. Very good. So base R addition is also simple. It's similar to our decimal addition. No worries. Okay. Let us have another addition in base 6, right? 2, 4, base 6 plus 3, 3, base 6. And I'm expecting a result in base 6. What is your result? 4 plus 3 is 7. I cannot write 7 because it's a base 6 system. So I should subtract the base. So 4 plus 3 is 7. 7 minus 6 is 1. I should write a 1 here. All right, 101. Very good. Then to compensate that subtraction, I should add a carry. Right? 2 plus 3 is 5. 5 plus 1 is 6. 6 is not a valid symbol. 6 minus 6 is 0. To compensate that subtraction, I should add a carry. So 101. Very good. Right. Okay. Base R addition. So let me go for hexadecimal addition. AB plus CD. Base 16. Base 16. What's your result? AB plus CD in base 16. Then we'll take a break. Hexadecimal addition. Hexadecimal addition. What's your result? Similar to this, you should recall that hexadecimal, we are having 16 symbols from 0 to 9, 10 symbols here. Okay, 10. Then A, B, C, D, E, and F. Okay. A corresponding to decimal 10, B corresponding to 11, C corresponding to 12, D corresponding to 13, E corresponding to 14 decimal, F corresponding to 15 decimal. Okay, decimal. Right, very good. Anjan answered 178, George 178, Arvind 178, right, very good. So first addition is B plus D, right? B corresponding to 11, D corresponding to 13. So B plus D is 24. 24. I cannot Right, very good. I cannot write 24 here because I don't have a symbol corresponding to 24 decimal in hexadecimal. Okay, so I should subtract base, that is 16. 24 minus 16 is 8. So I should write 8. To compensate that subtraction, I should add a carry. A is corresponding to 10. C is corresponding to 12. 10 plus 12 is 22. Plus carry 123. I don't have a symbol corresponding to 23 in hexadecimal. So I should subtract the base. So 23 minus 7 is 7 decimal. So I should write 7 decimal. To compensate that subtraction, I should add a carry. So the third digits are zeros. So 0 plus 0 plus 1 is 1, 7, 8 hexadecimal. Hexadecimal, right? So you can add any number in a given base, right? But you should be careful. This number and this number both are in a same base system, and you are expecting a result in the same base 16 in this particular example, right? Okay, so we will have a short break after discussing one more problem. This is question number 5. Question number 5, right? After this, we'll take a break. Given that 135, 135 base x plus 144 base x equal to 323 base x, right? Find the value of x. Find the value of x. Options are given: A, B, C, and D. Options are 4, 5, 6, and 7. Right. Very good. It's 6. Yes, very good. It's 6. Right. So if you are not comfortable with the base or addition, then you should convert this into what? X square plus 3x plus 5 base 10. Okay. Plus again x square plus 4x plus 4 base 10 equal to right hand side 3x squared plus 2x plus 3. Right. Then you should solve this. You'll get it's a quadratic, so we'll get two values. One value will be 6. I don't know about the other value, right? But if you're comfortable with the base or addition because all are in same base, okay, it's nothing but 135 base x plus 144. And we are expecting this result, that is 3, 2, 3. So if you're adding 5 and 4, you are getting a 9. Instead of 9, you are writing 3. So you are subtracting 6 and adding a carry. 3 plus 4 is 7 plus 1 is 8. 8 minus 6 is 2. So you are adding a carry. So 1 plus 1 plus 1 is 3. So addition is right. So the right option is 6. Right. Otherwise, you have to take equivalent, decimal equivalent, add it together equal to the decimal equivalent of RHS, then solve for your x. You will get two values for x because it's a quadratic, and one value will be 6. And anybody, what is another value? Which number it is? Positive or negative? If you are going for a conventional method. No, you need not do that actually. So this is a quick method. You can directly go for base 6. Okay. Is that clear up to this base or addition? We have a lot more problems to discuss today. We'll complete that. Then we will get into representation of a number, 1s, 2s, complement representation. Then r's complement and r minus complement, r minus 1's complement, 3's complement, 4's complement, 6's complement. Those things also we'll discuss today. Okay, right. So last problem answer is 6. We'll take a short break and we'll meet after 19 minutes. So we'll meet at 7. Okay. All right. Okay. See you then. Shall I continue? Everyone is back. Yes. Okay. So let us have another question. Question number 6. Given that 302 base r upon 20 base r equals 12.1 base r. Find the value of r. And you are given with the options 4, 5, 6, and 7. 302 base r divided by 20 base r equal to 12.1 base r. So division we are not comfortable with, so we have only one option. Convert this numerator into decimal, denominator also into decimal, right hand side also into decimal, then solve for r. So numerator will be 3r square plus 2 upon 2r equals, this is decimal equivalent, and this is also decimal equivalent. The right hand side you should be careful, it is r or 1 into r, 1 multiplied by r plus 2 multiplied by r power 0. You should not forget to put an or sign, plus 1 multiplied by r power minus 1. That many decimal equivalent base 10. Right, very good. Prince is answering 4. Very good. So this will be 3r squared plus 2 upon 2r. Right hand side will become r plus 2 plus 1 over r. Taking this into the right hand side, 3r squared plus 2 equal to, this will become 2r squared plus 4r plus 2. So that will give me r squared minus 4r. These two will cancel each other, equal to 0. R multiplied by r minus 4 equal to 0, implies r equal to 0 or r equal to 4. So 0 cannot be the base, so right option, as Princey said, it's option A, 4. So you should not forget about this. After a fraction, it's an addition. Okay, so plus the digit 1 multiplied by base power minus 1. Right? Everybody did this? Any issues? Any confusions? Yes? Please respond. Right. Done? Okay. Shall I move to next one? Okay, right. Thank you. Okay. So let us have another question, another variety of question. Okay, question number 7 it is. Question number 7. Given 73 base x equal to 54 base 5. Sorry, 54 base y. Sorry, 55 base, sorry, 54 base y. 54 base y. Then the possible the possible values of x and y are, then the possible values of x and y are four options: x and y values. They are, first option says 8 and 11. Second option says 9 and 13. Third one, 10 and 12. Fourth one, 8 and 16. An equation is given. Left hand side is base x. Right hand side is base y. Then the possible values of x and y are four options. Possible values of x and y are four options. Right. F is answering option A. Very good. What about others? Right. Right. Option A. Very good. Very good. Okay. Right. Right. So we don't have any other options. So we should convert into, because they are in different bases. So we should convert into decimal equivalent or any other base equivalent. So it's better to convert into decimal. So this is 7 times base 7x plus 3 times x power 0, that is 3 decimal, equal to 5y plus 4 times 5 power 0, that is 4 itself, decimal equivalents. Then rearranging this, 7x minus 5y minus 1 equal to 0, or 7x minus 5y equal to 1. So that is satisfied for option A, right? Option A. So from this, you can also conclude that x should be greater than 7 and y should be greater than 5. But all options are greater than 7 and greater than 5. Because I have used 7 here, so base should be greater than that, simple. I have used 5 here, so y should be greater than 5. Okay, right, option A, very good. Right, so let us have another one. Another one is a direct problem, question number 8. Question number 8. 44 base 5 plus 33 base 6 plus 22 base 7 plus, let us say, 11 base 8 equal to x, y base 10. Find the values of x and y. Find the values of x and y. Four options: 40, 40, 60, 70, 80. So you should convert into decimal and you should find the decimal equivalent. Individual digits, x and y. Right, very good. Option C. Right, 70. Very good. Right, very good. Option C. Yes. Right. Adul said option C. Meenakshi also saying option C. Very good. Sitara, option C. George, Joseph, Aravind. 70. Option C. Very good. What about others? Around 60 students. Everybody is able to follow the class. Any other issues? I'm trying to identify your pace so that I can adjust my pace. Is that clear? What about others? Right. Okay. Shall I get into the other problem? Next slide. Then. Okay. Okay. Right. Okay. So we have another one. Let us say question number 9. Question number 9. The binary number is given. Let us say 1011010 is given. That is in base. Oh, this is too lengthy. So let us make it a simple one. Simple one. Let us say 1010 is given base 2. Okay. And you are asked to find the base 4 equivalent. Base 4 equivalent. Right. Base 4 equivalent. Identify the base 4 equivalent. And unfortunately, we don't have a direct method to convert two different bases other than decimal. Okay, other than decimal. So how to convert this? So we have only one option. This I should convert into decimal first. So 1, 2, 3, 4 digits. So 1 multiplied by 2 power 3 corresponding to 4 digits, and minus 1 is 3, plus second digit is 0, plus third digit 1 power 2, 1 multiplied by 2 power 1 plus 0, that many decimal. So this is 8 plus 2, 10 decimal, 10 decimal. Then the 10 decimal I should convert into base 4. So decimal number 10 I should convert to less base, that is base 4. So continuous division. So right, base 4, right, right, base 4. So 2 fours are 8, balance 2. I cannot divide 2 further with 4, so I should write as such 2. And it was from top to bottom or bottom to top? Bottom to top, right? Bottom to top. So 10 decimal is equivalent to 2 base 4. 2 base 4. Right, 2 base 4. Okay, instead, if you're having 4 digits, no problem. If you're having 8 or 10 or 12, 16 digits here, then it will be a lengthy process. The decimal number is going to be a larger number, then you have to divide more. So instead, if you're taking 2 digits, the combinations are both digits can be 0, 0, 1, 1, 0, or a 1, 1, right? In binary, 2 digits. So if you are identifying the decimal equivalent of this, both are zeros, so 0 decimal equivalent. 0, 1 will give you 1 decimal equivalent. 1, 0 will give you 2 decimal equivalent. 1, 1 will give you 3 decimal equivalent. So if you're comparing with a base 4 system, right? Base 4 system, right? Here it is a base 4. The base 4 system will have 4 symbols including 0, 0, 1, 2, and 3. So the given binary number, you can branch from the right side like this. So 1, 0 corresponding to 2 decimal, and that 2 decimal is same in base 4. Base 4 number 2 decimal is same as 2 in base 4, right? Single digit. So 1, 0 base 2 is same as 2 in base 4. So I can directly write, instead of 1, 0, I can write a 2. So this 1, 0 will give me 1, 2. The other one will also give me another 2. So directly you can write it as 2 to base 4. Right? That will be helpful if you're having a larger number like this. Like this. equivalent base 4 number. This is in binary, right? Then you can easily group it from right side. This one, another one, another one, another one, another one. By default, you can put a 0 here. So this corresponding to 2, this 0, 1 corresponding to 1, 1, 1 corresponding to 3. Look here, 1, 1 corresponding to 3, 0, 1, 1, 0, 1, 1, 0, 1 corresponding to 1. So this is equivalent to a base 4 number with the digits triple 1, 3, 1, 2, base 4. It's quite simple, right? Is that clear? You need not do this conversion and then this continuous division. So directly you can branch it, right? How to branch, why it is true, everything you will discuss. No problem. Why we are not branching with the 3 digits instead of 2 digits, that we'll see later, right? Is that okay? Did you copy this? Shall I move to next one? Yes? Okay, right. So let me have another one, question number 10, right? In which I have another binary number 1010110110 base 2. You should evaluate its base 8 number. Base 8 equivalent. Base 8 equivalent. Please note that initially it was from 2 to 4. Now it is from 2 to 8. Right? So base 8, we know that 0, 1, 2, 3, 4, 5, 6, 7. Total 8 symbols. And to represent a to represent a 7, we require how many binary digits? 3 digits are required, right? So 0 is 000, 001, 010, 011, 1004, 101, triple double 10, and a triple one. This is decimal 7, right? 4 plus 2 plus 1, 7. This is 4 plus 2, 6. This is 4 plus 1, 5. This is 4. This is 2 plus 1, 3. This is 2. This is 1. And this is 0. Decimal. So here you should branch 3 digits at a time. Okay, 3 digits, right? Very good. 2556, right? So 3 digits, 3 digits, 3 digits. Here you can insert a 0. So this corresponding to 10 is 2, 101 is 5 here, here also 5, 110 is 6. So it is 2556. Very good, right? If it is in base 16 number, okay, 16 number, we should recall that 2 and 4, so 2 power 2 was 4, so we are looping, branching 2 digits at a time. In our second problem, 2 power 3 was second base 8, so we are branching 3 bits at a time. If you're going for 16, it's nothing but 2 power 4 is 16, right? So we should branch 4 digits. So 4 digits at a time implies you will have this 4, right? And then another 4 here. Then you can insert a 0, you'll have another 4 here. Okay. So 1110. First one is 1110. Not 1110, 110. Right. 110. What is the value of 110? No, it is 1110. Correct. I am looping 4 digits at a time. Sorry. 1110. What is the value of 1110 in decimal? 1110. Means this is 8, this is 4, 12, this is 2, 14, right? So this is 14 decimal. What is the hexadecimal equivalent of 14? Hexadecimal, please recall that you're having a symbol up to 9, then A, B, C, D, E, and F. F corresponding to 15 decimal, E 14, D 13, C 12, B 11, A 10. Right? So your 110 is 14 decimal. The simple corresponding to that is E, right? 14 decimal. So this one is E, right? The second branch is 0, 1, 1, 0. That is 6. 6 is 6 itself because 6 lies here, right? The other branch is, no, it is not 6. Let me check this. 0, 1, 1, 0, right? It's 6 only, right? 6, 0, 1, 1, 0. So this is 6 decimal. So 6 itself, right? 5, 6, E, right? Very good. And the last one is 0, 1, 0, 1. 0, 1, 0, 1. This is 5 decimal. So that is 5 itself. So 5, 6, E, base 16. Right? If you are asked to find the base 32 equivalent, base 32 equivalent of this number. Let me rewrite that number here. Right. It is 0, 1, 0, 1, 0, 1, 1, 0, triple 1, 0. 2 power 5 is 32, so I should branch 5 digits at a time. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. So 0, 1, 1, 0 is 14 decimal. Right. So the digit, I will take it as E itself, because 14 decimal, let us assume in base 32 system, 14 decimal will have a symbol E. Then I should write E here. Okay, E. Then next one is 0, 1, 0, 1, 1. 0, 1, 0, 1, 1. How much is this? This is 2 power 0, that is 1. This is 2 power 1, 2, 2 plus 1, 3. This is 2 power 2, this is 2 power 3. So 8 plus 3, 11. Right, 11. 11. 11 corresponding to the digit B here. So I'm assuming base 32 has the same symbol B corresponding to decimal equivalent of 11. So I'm writing B here. Then this is a simple one. I have to branch 5 digits at a time. So I'm inserting 3 zeros. 3 plus 2, 5. Right? 0, 0, 1 is nothing but 1. So 1 BE base 32. Base 32. Okay, is that clear? So that is valid if two bases are related by 2 power n. Then number of digits that we are going to branch is equal to this n. Right? So 560 base 16 is correct. 1BE base 32 is also correct. Right? Base 32 will have 32 symbols. We have listed only 16 symbols here up to F. Then G, H, I, J, K, L, M, N, O, P, Q, etc. up to 32 symbols. Highest symbol decimal equivalent will be 32 minus 1, that is 31 decimal. Right? Is that clear? So you need not convert into decimal, then divide to obtain the respective base equivalent numbers. Yes, correct. Shall I move to next one? Is it clear? Any doubts? Yes, please respond. We have 30 more minutes. Is that clear? Okay. Okay. Right. Okay. Then we'll get into R's complement and R minus 1's complement. R minus 1's complement. R's and R minus 1's complement. Okay. Where R is the base. R is the base. So atom Fourier base, the lowest base is R equal to 2 on R equal to 2, smallest base. So for binary system, we'll have 2's complement and 2's complement, that is R's complement, and R minus complement will be, R minus 1's complement will be 2 minus 1's complement. 2 minus 1 is 1, so 1's complement. right? It is easy to take the complement of a given number. It's nothing but a digit-wise subtraction. So if you are trying to identify the r's or r minus 1's complement of a number n, right? R minus 1's complement of a number n, number is n, so I'm going to find r minus 1's complement, right? So you just write r minus 1 here, okay, r minus 1, then subtract that number from that, you will get r minus 1's complement, right? R minus 1's complement, okay? Once r minus 1's complement is ready, then you can take r's complement by adding 1 with r minus 1's complement. Okay. If it is not clear, we'll have some problems. Then it will be clear. So base minus 1, individual digit-wise subtraction, right? So let us take an example. Let us take 1010 in binary. I should find r minus 1's complement, that is 1's complement. Then I should write how many digits are there? 1, 2, 3, 4. So I should write 4 r minus 1's values. R is 2, r minus 1 is 1. So 1, 2, 3, 4. Then I should take a digit-wise subtraction of the given number, right? So 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0. So 1's complement of this 1, 0, 1, 0 is 0, 1, 0, 1 as expected, right? If you are interested to calculate 2's complement, you should add a 1 with this. So 1 plus 1 is 0, carry 1. 1 plus 0, 1, then 1, then a 0. Right? So 0, 1, 1, 0 will be its 2's complement. Okay? Don't worry, don't worry. You'll have another problem. Okay? Did you copy this? Right? I think Aditya is asking me to repeat. Right? I will repeat. No problem. Right? I think all of you copied. Okay. So let us have another number. Let us say 2, 1, base 3. Okay, please listen. 2, 1, base 3. Here r is 3. Okay. So if r is 3, I will have two complements, r minus 1's complements and r's complements. So r minus 1's complement is 2's complement. It's a base 3 system. And r's complement is base complement or 3's complement. Right? To obtain r minus 1's complement, it's very simple. I should write base minus 1, right? They are 2 and 2. And we have 2 digits. So 2 times I should write 2, 2. Then I should subtract digit-wise the given number. So 2 minus 1 is 1. 2 minus 2 is 0. So the 2's complement of 21, 3, its 2's complement. 2's complement will be 0, 1, base 3. It's very simple. So if you are trying to get 3's complement, you should add a 1 with your 2's complement in base 3. So 1 plus 1 is 2. 0 plus 0 is 0. So 0 to base 3 is your 3's complement. So this is your 3's complement and this is your 2's complement or r's complement and r minus 1's complement. Okay, clear, right? And let us take the complement 2 times, right? I had a number 2, 1, base 3. I took its 2's complement. I got it as 0, 1, base 3. If I'm taking 2's complement of 0, 1 again, I should subtract 0, 1 from 2, 2. So 2 minus 1 is 1. 2 minus 0 is 2. So 2, 1, base 3. I will get the same number. So if you're taking complement twice, you are getting the same number. Similarly, if you are taking the 3's complement twice, that is, you should take 2's complement first of this result, 0, 2, right? 2 minus 2 is 0. 2 minus 0 is 2. To get a 3's complement, you should add it. Add a 1. So 2, 1, base 3. Same as this number. So if you're taking r's complement twice, you will end up with the same number. Again, if you're taking r minus 1's complement twice, you will again end up with the same number. Okay, that is very simple. Digit-wise subtraction. Okay, right? Clear? Done? Yes, please respond. R's complement and r minus 1's complement. Clear? Okay, right. Right, okay. So let me have one more example. The 9's complement of 1, 2, 3, 4, 5, base 10. The 9's complement will be 9, 9, 9, 9, 9 minus the number digit wise. 9 minus 5, 4, 9 minus 4, 5, 9 minus 3, 6, 9 minus 2, 7, 9 minus 1, 8. Decimal. That is, it's 9's complement. If you're adding 1, you will get 10's complement. So 10's complement will be 87655 decimal plus 1 will give me 10's complement. Okay, right. So let us move into the representation of a number. Or before that, we'll have a short discussion about 2's complement. Okay, so 2's complement, because that 2's complement is important in our number system representation, right? So 2's complement will have a few more examples. Let us have a one number 1 0 1 0 1 1. Obtain its 2's complement. Obtain its 2's complement. It's very simple. You should take 1's complement first. 1's complement will be 0 1 0 1 0 0 plus 1 will be your 2's complement. So 1 0 1 0 1 0. So 2's complement is 0 1 0 1 0 1. Okay. If you're taking the 2's complement of 1 0 1 1 0 0, you should take 1's complement first, 0 1 0 0 1 1. Then you should add a 1. So 1 plus 1 0, carry 1. 1 plus 1 0, carry 1. 1 plus 0 1 0 1 0. So it is 0 1 0 1 0 0. If I'm taking 1 0 0 to its complement, I should take 1's complement first. Then I should add a 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 0 is 1. So 2's complement is 1 0 0 itself. Right. If I'm taking 1 1 0 0, I should take its 1's complement first, 0 0 1 1. Then add a 1. Okay, add a 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 0 is 1, 0. So this is nothing but 0 1 0 0. Okay, if I'm taking 1 4 zeros, its 2's complement will be same 1 4 zeros, because I should take 1's complement first, that is 0 1 1 1 1. I should add a 1. I will get 1 plus 1 0, carry 1. 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 1 plus 0 is 1. So saying 1 0 0 and 0 0. So to identify 2's complement, we have a simple shortcut, right? Observe the given number. You travel from right to left, right to left, right to left, right to left. You repeat the number until you're observing a 1. So first here I am observing a 1. So I'm repeating up to that. Then you should complement individual digits, right? This 1 I am complementing to 0. This 0 I am complementing to 1. This 1 I am complementing to 0. This 0 I am complementing to 1. This 1 I am complementing to 0. Start from right extreme towards left, travel towards left. Repeat the patterns until you are observing a 1. After that, just complement the individual digits. Let us take second case. Travel from the right extreme. I'm traveling it 0. So I'm repeating that because I didn't observe a 1. Again, I'm observing a 0. I'm repeating that. Again, I'm observing a 1. I'm repeating that. Then I should complement. So instead of 1, I should write 0. Instead of 0, I should write a 1. Instead of 1, I should write a 0. So this is my 2's complement. Okay. Listen carefully again. Travel from right extreme towards left. Repeat until you are observing a 1. Here I am observing a 1. So I'm repeating up to this. So 100 is same as 100 to us. 1100, I'm repeating up to first 1. Then I'm complementing this 1 with a 0. Similarly, here I'm traveling towards left. I'm repeating until I am observing a 1. I'm observing a 1 here. So I'm repeating to that. So that is a simple shortcut to identify 2's complement of a binary number. You need not take 1's complement, then add a 1. That is a lengthy process. So directly you can write the 2's complement of that particular binary number. Is that clear? If this is clear, we will get into representation of a number. I request 15 minutes to explain that, then we will wind up. Is that clear up to this? 2's complement, 3's complement, 4's complement, etc., r's complement, and r minus 1's complement. Is that clear? Okay. Please respond. Because as I said, we don't have a face-to-face contact, so I cannot identify whether you are comfortable or not. Only chat window is the option. So please put Y or yes or bit fast. It's clear. Okay. A bit fast. Others saying it's a bit fast. Okay. I will take care. No problem. Okay. All right. Okay. So representation of a number. Okay. Representation of a number. This is important. You can expect one question from this. Right. Representation of a number. Right, please listen carefully. You'll get 1 mark. Representation of a number. Before getting into the representation of a number, let me tell you, we have 1, 2, 3 representation. So actually we have more representation, but here we are going to discuss only 3 representations. One is 1's complement representation. Second one is 2's complement representation. Third one is signed magnitude representation. Or I will take the order the other way. First one we'll discuss signed magnitude. That is very simple. Then we'll go for 1s representation. Then we'll go for 2s or 2's complement representation. Okay. So I'm requesting your attention for 3 to 4 minutes. Okay. Right. So I'm taking a 3-bit example. It is easy to convey with an example. So I'm taking a 3-bit case example. Right. We are going to represent a number using 3 digits in binary or 3 bits in binary. Right. We are going to represent a particular number using 3 digits in binary. And all of you know that if I'm using three digits, I can have eight combinations, eight number of combinations, right? 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and a triple 1. So this one is the pattern available with me. Okay, pattern, right? And we have three different representations: signed, magnitude, ones complement, and twos complement. So I'm trying to include them in different columns. Okay, right. This is my pattern. Okay, right. So please listen. Right. One of your friend has stored a number in this pattern, right? But he has the option to store using different schemes or different methods, right? They are either he can go for a signed magnitude representation using 3 bits or 3 digits, or he can go for ones complement representation using 3 digits, or two's complement representation using 3 digits, right? So to identify the actual value of these numbers represented, your friend should tell you that which scheme he has used, right? So suppose he's saying that he used a scheme that signed magnitude representation. Then it is very simple. If it is a signed magnitude representation, it's very simple. First digit or MSB digit corresponding to sign bit. Okay. The remaining n minus 1 digits, here it is 2, represents the magnitude. So if MSB is 0, implies the number is positive. Number is positive. Number is positive. Number is positive. In signed magnitude, 1 bit MSB dedicated for a sign bit. And if it is 1, it implies it's a negative number. Negative number. Negative number. As I said, the other 2 digits represents a magnitude. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, and a 1, 1 with a negative sign. Right? So let us identify the magnitude and sign. Sign we have identified already, right? So it's a positive number. Okay, first one is a positive number. What is the magnitude? 0, 0 implies decimal equivalent is 0. 0, 1 implies decimal equivalent is 1. 1, 0 implies decimal equivalent is 2. So it's a positive 2. 1, 1, 3. So positive 3. Okay, that is very clear. Very simple. And the remaining numbers, we are having same magnitude, but different sign. So minus 0, minus 1, minus 2, and a minus 3. So the patterns from 000 to 111, if the scheme used or the method used is assigned magnitude representation, then 000 to 111 will have the values positive 0, positive 1, positive 2, 3, negative 0, negative 1, negative 2, and negative 3. Right. And that is over. Then your friend is saying that that is not correct. Actually, I have used ones complement representation, not signed magnitude. Then let us check how to identify the actual number if the person used a scheme called ones complement representation. Okay. This is also very simple. Similar to signed magnitude, if MSB bit or most significant bit, MSB bit, is 0, the number is positive. Number is positive. Number is positive. Number is positive. If MSB is 1, the number is negative. So it is negative, 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 negative because all digits are 1, right? So if it is in one's complement representation, if the number is positive, then it's very simple. The magnitude is evaluated by using all available digits. Here it is 3. Entire digits will represent the magnitude. Okay, so 000, 001, 010, 011, right? If number is positive, the same pattern is taken for obtaining its actual value, decimal equivalence. Okay, right? So let us check first one. Positive 000 is equivalent to 0 decimal, so plus 0. This is positive. 001 is 1 decimal. 010 is 2 decimal. 011 is 3 decimal. Right? If the number is negative or MSB bit is 1 and the scheme used is 1's complement representation, then before identifying the magnitude, you should take the respective complement of the pattern. The pattern here is 100 and the scheme used is 1's complement. So I should take 1's complement of that pattern, that is 011. Flip 1 with a 0, 0 with a 1, that is 1's complement, right? 111 minus 100, 1 minus 01, 1 minus 01, 1 minus 10. So just flip it, that is 1's complement. Again, here also the number is negative. So I should take 1's complement before obtaining its actual decimal equivalent value, right? So 101 decimal equivalent is 0, sorry, 1's complement is 010. 110, its decimal equivalent, sorry, its 1's complement is 001. 111, its 1's complement is 000. Then go for their equivalent decimal values. The number is negative, so I should put a negative sign. 011 is 3, so minus 3. 010 is 2, so minus 2. 011 is, sorry, 001 is 1, so it's a minus 1. 000 is 0, it's a minus 0. So note that I have a positive 0 and a negative 0 here, similar to a positive 0 and a negative 0 in signed magnitude, right? I have one more representation, 2's complement representation. Then your friend is again saying that no, it's not signed magnitude, it's not 1's complement, it is actually 2's complement representation. And then also it is very simple to identify. If MSB is positive, if MSB is 0, number is positive. MSB 0, number is positive. MSB 0, number is positive. MSB 1, number is negative, number is negative, number is negative, number is negative, right? So if number is positive, I don't have any confusion. Similar to 1's complement method, I will use the entire 3 digits to evaluate its magnitude. So 001, 010, 011, please listen, 011, right? All positive numbers. I'm using the same pattern to identify the magnitude. So I can easily arrive the magnitude. It's a positive number. So positive 0, positive 1, positive 2, positive 3. Done. If it is a negative number, in the case of 1's complement representation, we took 1's complement of the pattern. This is my pattern before arriving the decimal equivalent. So here, if it is a 2's complement representation, I should take 2's complement of the pattern, right? So we know that 100, 2's complement will be traveling from right extreme towards left. Repeat until you are observing a 1. So it is 100 itself. Traveling from right extreme towards left. Repeat until you are observing a 1. Then complement individual digits. Okay. Travel from right extreme towards left. Repeat until you are observing a 1. then complement the digits, right? Triple one, travel from right extreme towards left, repeat until you're observing a 1, then complement your digits. So I have taken this complement of the pattern before evaluating its magnitude because the numbers are negative. The reason for that is its MSPs are 1. Okay. So 100 is a 4 with a negative sign. 100 is equivalent to decimal 4. 011 is decimal 3 with a negative sign. 010 minus 2. 001 minus 1. So here you can observe that positive 0, negative zeros are absent. Only positive 0 is present. Only positive 0 is present. Negative is absent. Instead of negative 0, I have one more extra range, that is minus 4. So the number 0 is represented as a triple 0 in all three cases, right? 1 is represented as 001 in all cases. So no issues with positive numbers, right? Same values. If the number is negative, you should put a negative sign and take remaining n minus 1 digits while evaluating magnitude in the case of signed magnitude representation. If it is a ones complement representation, take a negative sign. Then before evaluating its magnitude, take the ones complement of the pattern. Okay. So similarly, if it is a two's complement representation, take the pattern. If MSBs are zeros, no issues. Positive sign, entire pattern, same magnitude. If MSBs are 1, number is negative, then before taking the magnitude, you should take 2's complement of the given pattern, right? So 2's complement representation, you can represent from minus 4 to positive 3. Signed magnitude and 1's complement, you can represent from minus 3 to plus 3. 2's complement representation, you're having only one zero, positive 0. The other representations, you'll have two zeros, positive and negative zeros. Okay. The one bit dedicated for sign bit, and that bit is most significant bit, MSB, dedicated for sign bit. If MSB equal to 0, the number is positive. Remaining n minus 1 digits will decide its magnitude. Similarly, if MSB bit is equal to 1, the number is negative, and the remaining n minus 1 digits will decide its magnitude. Whereas in the case of one's complement representation, if the given pattern MSB is equal to 0, that implies number is positive, the entire pattern will decide its magnitude, and bits will decide its magnitude. Whereas if the MSB bit of the given pattern is 1, that implies the number is negative. Then before evaluating its magnitude, we should take one's complement of the entire digits. Similarly, in the case of two's complement representation, if the number is positive, that implies MSB bit will be 0, right? Then the entire digits will decide its magnitude. If the MSB digit is equal to 1, that implies the number is negative, then we should take 2's complement of the given pattern before evaluating its magnitude. And we also discussed an easy method to identify the 2's complement of a given binary number. Travel from right extreme towards left. Repeat until you are observing a 1. Here I am observing a 1 here, so I'm repeating up to that. Then complement each digits 1 to 0, 0 to 1, 1 to 0, 0 to 1, and 1 to 0, etc. Another example 10000, 10 11 00 here, 10 11 00. Start from right extreme, travel towards left. Until you're observing a 1, you repeat the bit patterns. So I'm repeating up to this one here, here. Then complement individual digits. So this 1 to 0, this 0 to 1, and this 1 to 0. Right. So similarly, the number, the pattern, let us say triple one here will corresponding to a minus 1 because MSB is 1, so the number is negative. Then while evaluating the magnitude, you should take the 2's complement of triple one. That is very easy. You should travel from right extreme towards left. Repeat until you're observing a 1. First I'm observing a 1, then complement the remaining digits. So 001. So 001 is the magnitude. So 001 is the decimal equivalent is 1 decimal with a negative sign. Okay. So three different representations. And you please note that in your signed magnitude representation, I could represent from -3 to +3, including two zeros. Okay. Similar to that, in the case of one's complement representation, +3 and -3 extreme values, and again two zeros. Whereas in the case of two's complement representation, using three digits, right? I'm using three digits, 1, 2, and 3. Three digits. I could represent from -4 to +3. One extra range, -3 to -4. I can represent up to -4 in the negative axis and up to +3 in the positive axis. And I have only one representation for 0, +0. So if n equal to 3, n equal to 3, you can represent up to -3 to +3 in the case of signed magnitude. Again, if n equal to 3, in the case of one's complement representation, you can represent up to +3 from -3. Whereas in the case of two's complement representation, if n equal to 3, two's complement representation, I can represent from -4 to +3. Right? Okay. So similarly, if I'm using 4 digits, I will be able to represent from -7 to +7. Then again, -7 to +7, +7. Here, -8 to +7 if n equal to 4, right? And you please tell me what is the pattern corresponding to -3 in signed magnitude with n equal to 4. What is the pattern corresponding to +3 in signed magnitude with n equal to 4? And pattern corresponding to -7 in the case of one's complement and +7 in the case of one's complement. Similarly, -8 in the case of two's complement and +7 in the case of two's complement if n equal to 4. I'm expecting your answers. The representation of -7 +7 -8 +7 in signed magnitude, one's complement, and two's complement representations. Am I audible? Yes? Okay, Princey initially told me that not audible. Right, I think it's audible. Okay, right. Thank you. Okay. Right. So what is the pattern corresponding to -7 in the case of sign to magnitude using n equal to 4 digits? What is the representation? The number is negative. Right. Number is negative, so MSB should be 1. The remaining digits will decide its magnitude. So again, triple one. So double one will be -7 in the sign to magnitude representation. Similarly, positive 7 implies positive 7 in sign magnitude. Number is positive, so it must be 0. Then the remaining digits will decide its magnitude. Triple one will give me 7 decimal. Right? Again, what is -7 in one's complement representation? -7 in one's complement representation. What is the pattern corresponding to -1 in, -7 in one's complement representation? Please provide your answers. Is it 1 0 0 0 or 0 1 1 1? -7. -7 implies the number is negative, hence MSB should be equal to 1. Right? MSB should be equal to 1. Then I have told you if the number is negative, before taking the magnitude, you should complement the entire pattern. Right? We are trying to identify the pattern that represent -7 in one's complement representation. Right. So if you're taking one's complement of that pattern, you should get 7 as its magnitude. Right. So what's your answer? Is it 1 0 0 0? So if it is 1 0 0 0, right, this is a pattern, and this one implies the number is negative. Before taking the magnitude, if the number is negative, I should take the respective complement. The representation is 1s, so I should take 1's complement. So this is -7 in 1's complement representation. Right? What about +7 in 1's complement representation? +7. +7 in 1's complement representation. +7. Yeah, it will be, number is positive, so MS will be positive. And then if the number is positive, the entire bit pattern will give me the magnitude. So the magnitude should be 7. So it should be 0 1 1. Right? So the positive same pattern will give me the magnitude. So this is +7. Right? In your 2's complement representation, I have a number here that is -8. What is the representation of -8? Using n equal to 4. So the number is negative. So of course the MSB bit will be 1. Then if you are taking the 2s of that, you should get a magnitude that should be equal to 8. 8 decimal in binary is 1 0 0 0. That is 8. Right? Right? Then if it is 1 0 0 because 1 0 0 2's complement will be 1 0 0 itself. So it's nothing but 1 0 0. MSB is 1, so the number is negative. And I should take a 2s of the pattern. The pattern is 1 0 0 before evaluating its magnitude. So 2s of 1 0 0 is 1 0 0 itself, because I should travel from right extreme towards left. Until I am observing a 1, I should repeat. So I'm repeating up to this 1. So 1 0 0 pattern will give me -8 in 2's complement representation using n equal to 4, using 4 digits. Right? 0 1 1 is wrong. 0 1 1 is +7. And 1 0 0 will be -8. What about positive sign? Sorry, +7 in 2's complement representation using 4 digits, plus 7 in 2's complement representation using 4 digits. So MSB should be 0 because the number is positive. Is it 0001 plus 7? Is that 0001? MSB is positive. If MSB is positive, you need not do anything. The entire pattern will give you the magnitude. Is it 0111? Positive 7 into its complement representation. This is my positive 3, and this is my pattern, right? Is it 0001 or 0111? Right. So this is nothing but 0111, right? Because the number is positive, so I should not take the complement. So it's 0111 itself. So this is positive 7. Okay, 7. Right. So if n equal to 3, n equal to 3, I could represent a number that is minus 3 to plus 3 in sign to magnitude, minus 3 to plus 3 again using 1's complement, minus 4 to positive 4 using 2's complement representation. Similarly, if n equal to 4, I could represent again minus 7 to positive 7 here, minus 7 to positive 7 here, minus 8 to positive 7 here in 2s. So in general, your signed magnitude representation and 1s representation both are same. You can represent a number ranging from minus 2 power n minus 1 to a positive number range, positive range, positive number range, positive 2 power n minus 1 again, in the case of both the signed magnitude and 1's complement representation, using n digits, n digits, n digits. So that's a general form using n digits, right? Aravind is asking a query. So for 1s and 2s complement representation, the largest negative magnitude comes to the first number when MSB is 1. Largest negative magnitude comes to the first number when MSB is 1. So let me check. I'm not able to follow your query. The largest negative magnitude comes to the first number when MSB is equal to 1. So I couldn't identify your question. Okay. Okay. That we'll discuss.
Sir, what I
Right.
meant was
Yeah.
when considering the original pattern,
Okay. Okay.
not the representation itself, when considering the original pattern.
You're talking about this pattern,
Yes,
or
yes.
yeah. Okay. Then if largest negative magnitude comes to the first number when MSB is 1. MSB is 1, these 4 cases. And the largest magnitude comes, okay, you are saying that 100, the largest magnitude is, correct?
Yes, for the negative magnitudes.
Yeah, that is correct. In this order, the first negative number will give you the largest magnitude. That is correct. Right. Thank you.
Okay, sir.
Okay, right. So this is the general expression for one assigned magnitude. Similarly, you are having one extra range if it is a 2's complement representation using n digits. Okay, n digits. It is from minus 2 power n minus 1 to positive, same range, n minus 1 minus 1. Right, so 2 raised to n minus 1. Okay, so that you can keep in your mind. Okay, right. So let us have one or two questions based on this. Okay, right. So what is the decimal equivalent of three numbers represented in 2's complement format. These are three numbers represented in 2's complement format. You should identify their values, including sign. Three numbers are represented in 2's complement format. You should identify the number in decimal equivalent, including its sign. So this number is negative because MSB is 1, and I'm talking about 2's complement representation. So the pattern will be same as this. Okay, same as this. So it's minus 4. This is also number is negative, and I should take the 2's complement. Same pattern will be its 2's complement, right? So it is minus 8, right? The number here again, number is negative, and the representation used is 2's complement representation. So I should take the 2's complement of that number. It is 00010. So that is same as minus 8. So these two will give me the same number, right? So the second number, actually the first number was 1000. 1000. The second number I have extended the sign bit. Okay, so this was minus 8. This also minus 8. If I'm extending sign bit again, right, still I will get minus 8. If I'm extending again, still I will get minus 8. So if you are extending the sign bit, the value of the number won't change, right? If you are extending the sign bit, the value of the number won't change. Okay, that also you can keep in your mind using examples, right? 100 minus 4, 1000 minus 8, 11000 also minus 8, right? Right, I'm moving to next one. Please tell me what is a representation of minus 1 decimal, in 2's complement representation. Okay, 2's complement representation, 2's complement representation using 16 bits, using 16 bits. You should represent a minus 1 decimal in 2's complement representation using 16 number of digits or 16 bits. Please note that you are going to represent a negative number. So the MSB bit will be 1. And you should use 16 number of digits. What's your answer? How much is your answer? Is it all ones? 1, then all zeros, then A1? Right? How to identify? Right? Okay, all ones, then and 01. George says ones, then last 01. Hindu also says 1101. Okay, all right. All right. So you're saying 14 ones, 1, 2, 3, 14 ones, and then 01. Okay, this is a representation, right? You said this is a representation. Three of you, Hindu and George saying that it's a continuous one, then a 0, 1. So if this is a representation using 2's complement, MSB is 1, so the number is negative. Right. Then all ones. Anjana says all ones, right? Very good. Then before evaluating the magnitude, I should take the complement. Complement of what? Which complement? 2's complement, right? So I should travel from right extreme. Repeat until I'm observing a first one. Then complement the digits. Okay. So this is nothing but a -3 it is. Right. So to represent a -1 in a 2's complement representation, you require only one digit, right? Suppose you are using only one digit, n equal to 1. It's a simple one. Then it has must be equal to 1, right? Must be is equal to 1. So the number is negative, okay? And the representation is 2's complement representation. Then before evaluating the magnitude, you should take 2's complement of that bit. What is the 2's complement of 1? You should travel from right extreme towards left. You should repeat until you're observing a 1. So I'm observing a 1. I'm repeating that. So this is nothing but -1 decimal, right? So the pattern simple 1 will give me -1. So if I am extending my sign bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So 15 plus 1 total 16 digits. This will also will give me which one? Number is negative. I should take which complement? If the number is negative, 2's complement. So I should travel from right extreme, first one here. Then I should repeat. And that is a decimal equivalent. So that will give me -1. Or this is a -1 decimal. So if you're extending the sign bit, the number won't change. So using 16 digits, the representation is this one, right? So if you're branching it, or if you're converting into hexadecimal, this is F, right? This is another F. 4 ones will constitute a single digit because binary to hexadecimal conversion. 2 power 4 is 16. 16 is the base of hexadecimal. So you should branch 4 bits at a time, right? 1, 2, 3, 4 again. This will give me F. Yeah, this will give me another F. So F represents a 2's complement representation of -1. FF in hexadecimal also represents -1 using 8 bits. Then triple F hexadecimal also -1. Then 4FFF hexadecimal is also -1, right? So you require only one digit to represent a -1 in 2's complement representation. Okay, 2's complement representation. Right? Is that clear? Then yes. Right. So suppose if you are asked to identify the 2's complement of a fraction binary, let us say 101.101 base 2. It's a 2's complement. And the procedure is same to evaluate the 2's complement. You should travel from right extreme. Repeat until you're observing a 1. First I am observing a 1. Then complement the individual digits. 0, 1, and 0. Same procedure to evaluate the complement of a fraction. Right. So you can extend the same technique for fraction numbers also. And based on yesterday's class, I had a few requests to do the subtraction using base R subtraction. Okay, so we did base R addition. So let us take one example. So subtraction. Let us subtract AB minus 2A. AB minus 2A. Both are hexadecimal numbers. And what will be the result? If we are subtracting two hexadecimal numbers and I'm expecting result in hexadecimal. Right. Won't the sign be negative? Aravind is asking about a sign. Won't the sign be negative? Which sign you are asking about? No, this is not a number system conversion. This is just a binary number, just a binary number, and I took the complement of that pattern. That is not related to representation of a number. I didn't say a number is represented like this, and you should identify that number. Nothing like that. You have a simple pattern, binary pattern that includes a binary point or decimal point. And then if you're having this fraction point, then you may confused, but you need not confuse. You can extend the same technique, start from right extreme, travel towards left, repeat until you are observing a one, then complement individual digits. Okay, so this is not about identifying a number. It's just identifying a 2's complement of a fraction number. Okay, right. So let us come back to this. AB minus 2A. What is the result? AB minus 2A. Subtraction. It's very simple. B is the decimal equivalent is how much? 11, right? And A is 10. 11 minus 10 is 1. So I can write 1. No issues. A is 10. 10 minus 2 is 8. 81 hexadecimal, right? Suppose it is AB minus, let us say, 2F. Then what will be your result in hexadecimal? AB minus 2F. B is 11. F equivalent is 15. Highest symbol is F. Hexadecimal highest symbol will have the value base minus 1. 16 minus 1, that is 15. So we cannot subtract 15 from 11, right? So in decimal, if you are unable to subtract a digit from the other digit, then what is the procedure? We'll take a carry, right? Let us take example. Let us take 2, 3 minus 1, 9 in decimal. 3 minus 9, it is not possible. We'll take a carry. That 3 will become 1, 3. And then we'll subtract 9 from 13, right? 13 minus 9 is 4. Then this digit will decrement by 1. So 1 minus 1 is 0. So we'll get a 0 for decimal. Similarly, if you are trying to subtract F from B, you should take a borrow from the next higher digit. So the B will become 1B, right? 1B, right? Then you should subtract F. What is 1B? 1B is nothing but 1B base 16 is nothing but 1 into 16 plus what is B? B is 11. Okay. So 16 plus 11 is 27 decimal. So actually 1B is 27 decimal and you are subtracting F. F is equivalent to what? 15. So actually you're subtracting 15 from 27. Right. Right. Anjana, Ria, Aravind says 7C. Very good. So 27 minus 15 is 7 minus 5 is 2. It is 1, 2. What is 12 in hexadecimal? Simple. A is 10, B is 11, C is 12. So I should write a C. Then this A will decrement by 1. It will become how much? A is 10. Just before A is simple is 9. So 9 minus 2 is 7. Right. So as you said, it is 7C hexadecimal. So it's similar to a decimal subtraction, right? If you are not comfortable with if you are not able to write simply 1B minus F is C directly, actually if you are commonly using this hexadecimal subtraction, the moment B minus F, then you will write it as C, right? We should convert 1b into decimal, then subtract decimal equivalent of f, then 12, 12 convert back to hexadecimal, then you are writing C actually, because you are not familiar with this system. Whereas in binary, sorry, whereas in decimal subtraction, 3 minus 9, it's not possible. 1, 3, 13 minus 9, directly I will write 4, right? So here you should take this decimal equivalent, then take the subtraction, because you are not familiar with base 16 arithmetic. Whereas decimal, we are using it every day, so we are flexible enough. Okay, so that is a case of subtraction. You can apply, you can extend the method used in the decimal in the case of hexadecimal system also, right? So let us get into Boolean algebra. Okay, so this is all about number systems, right? This range is important. You please note this. Okay, range of numbers, right? Right. You can expect a question based on that. Okay, right. So let us have one more question based on that. How many? Let us have another question. How many? How many? How many? Then we'll get into Boolean algebra. How many digits? Digits, minimum numbers, minimum. How many digits, minimum numbers are required to represent 254 minus 254 decimal in 2's complement representation or 2's complement format. How many minimum number of digits are required to represent a minus 254 decimal in 2's complement format, or in using the best word is using 2's complement. I should write representation. 2's complement representation. 2's complement representation. Right? How many minimum number of digits are required to represent minus 254 using 2's complement representation? How many minimum number of digits are required to represent minus 254 using 2's complement representation? I'm expecting your answers. Answers? How to represent 254 minus 254 decimal in 2's complement representation? Two raised to 8 is 256, and 2 raised to 4 is 16. So the 15 decimal is same as 1111 binary. So 255 is same as 1, 2, 3, 4, 5, 6, 7, 8. Binary will give me 255 decimal. So 254 is 1 less than that. So 1, 2, 3, 4, 5, 6, 7, 0 is 2 is my 254. Right. Correct me if I am wrong. Right. And Aravind is saying that 7 is the answer. If it is 7, how will you represent a minus 254 using two's complement representation? 7 digits. What is the represented pattern of minus 254 decimal in two's complement representation? Okay, then what about others? Please try this. Try to write minus 254 decimal in a pattern using two's complement representation. That will give you minus 254. So MSB should be 1. Your pattern MSB should be 1. Okay, you will write a pattern and that MSB should be 1 because number is negative. Then if the number is negative, you should take 2's complement of that pattern while evaluating the magnitude. And the magnitude is this, I think, 0, 1, 2, 3, 4, 5, 6, 7. Let us check this. 0, 1. So this is 0, 1, 2, 3, 4, 5, 6, 7. So 2 power 7 plus 2 power 6 plus 2 power 5 plus 2 power 4 plus 2 power 3 plus 2 power 2 plus 2 power 1, right? 1, 2, 3, 4, 5, 6, 7, right? 2 power 1 is 2, this is 4, this is 8, this is 16, this is 32. I'm checking whether this is equivalent to 254 or not. 32, then this is 64, and this is 128. So 12, 14, 20, 28, 32, 34, 4, 7, 15, 11, 12, 13. Right. So Swati is answering 9. Right. Very good. Very good. So what is the representation then? If it is 9, how will it represent? Right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So using 9 digits, Ashok is saying that it will be, let us check, 1, then 6 zeros, right? 1, 2, 3, 4, 5, 6 zeros, 6 zeros, followed by 1 0, right? 9 digits. So he's saying this is the pattern. Okay, this is the pattern. So 1, 1, 2, 3, 4, 5, 6, 1, 6 zeros, then 1 0, 9 digits. So what we have discussed is number is negative, then I should take a 2's complement of this pattern. So how to take the 2's complement of that pattern? I should travel from right extreme. I should repeat until I am observing a 1. Then I should complement 1, 2, 3, 4, 5, 6, then a 0. One, complementing individual digits, right? And complementing this also. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So this is same as this. So that will give me minus, the value is 254, right? So 9 digits are required. Let us check that also. Our formula was minus 2 power n to positive 2 power, sorry, minus 2 power n minus 1 to positive 2 power n minus 1 minus 1, right? N minus 1 minus 1. That was our range of numbers using two's complement representation. right? That is correct. 2 raised to minus 2 raised to, let me check, minus 2 raised to n minus 1 to positive 2 raised to n minus 1 minus 1. Correct. That was the range. Okay. So if I'm substituting that, your answer was 9. So let me substitute for 8. So that will become minus to power. If your answer is 9, that will be 9 minus 1, 8, right? To the positive side, if your answer is 9, it is 9 minus 1, 8 minus 1. So 2 power 8 is 256. So you can go up to minus 256 to positive 256 minus 1. That is 255. So minus 254 comes in this range, right? So n equal to 9. If you are going for n equal to 8, you can represent only from minus 2 raised to n is 8. 8 minus 1 is 7 to positive 2 raised to 7 minus 1 if n equal to 8. So 2 raised to 7 is 128. So minus 128 to positive 127. So this minus 254 is outside this range. So minimum you recurse, as Ashok and Swati said, 9 digits. Okay, so that's all about number systems. Any queries? Then we'll get into Boolean algebra. Any doubts?